Alright, so this will be the last section for the class, actually, the last unit for the class. Unit 8, stoichiometry. A long word. Really all it means is just measuring elements. So we're to a point now where we understand what elements are. We can see that they form compounds. We can write the compounds. We can write balanced reactions that occur because of the combinations of those particular elements. And we can balance those reactions. Now we want to say, okay, if we start with so much reactant, and we combine it with another reactant, how much product might we form on the other side? Or, if we want to form a specific amount of product, how much reactant would we need in order to do so? Okay, so that's what this unit is going to refer to. First of all, we want to talk about mole relationships. Stoichiometry uses a reaction balanced equation, which gives how many. The coefficients in the equation tell us how many, to determine the masses, or how much, of products are formed. So the balanced equation equals the number of moles of each reactant and product, and that's what we refer to as how many. Stoichiometry then allows us to go from moles to mass and figure out how much, because we don't have a scale that measures in moles. We need a scale that measures, we obviously have scales that measure in mass, so we need a conversion that allows us to go from moles to mass. The idea here is that we've got an amount of reactants before a reaction, a certain amount of the red reactant, the one on the left right here, and the green reactant, the one on the right. And as the reaction occurs, we produce two new things. We've got the blue product and the purple product. And as you saw from the original reactants, you saw that there was much more of the red stuff than there's the green stuff, and so there's a little bit of red stuff left over at the end of the reaction. So stoichiometry is going to tell us, well, how much of the blue and the purple can we form, and how much of the red is left over. I think you can probably see that that's kind of important, because if you're a chemist and your boss is asking you to make something, you want to be able to predetermine how much you're going to be able to make with the reactants that you have, and how much leftover material you'll have at the end of the day. So to complete the stoichiometry process, we're going to use an approach called the BCA approach. BCA stands for before, change, and after. The BCA approach really emphasizes the balanced equation, so it's going to be really important that you can write a correct equation and balance that equation. And we're going to use the following as our example, just some hydrogen sulfide being burned in air, so adding to oxygen, sulfur dioxide, and water. And as you can see, the reaction is written correctly and it is balanced. So our table is going to look like this. We're going to have a before and a change above what we see as like a division line. And then below the division line, we're going to have the word after. Okay, so this is our little division line right here. So you've got a before, and you've got a change. Here's your before and change. And then here's your after below.
You know, you're stealing kids out of my math program, you know that.
All right, to continue. So we've got a before, change, and an after. We've got a balanced equation, and now we've got to see what type of math we have to do with this particular equation. Step 2. After we've balanced the equation, written the equation, wrote before, change, after, we need to fill in the before line. So if we remember from the problem, we had 2.4 moles of hydrogen sulfide gas. So we're going to write that in there, 2.4 moles of hydrogen sulfide gas, and you can see that it's right there. For the oxygen, the other reactant, we might ask, well, the problem says nothing about the amount of oxygen. But remember, this stuff is being burned in air. So I don't think it's a stretch for me to convince you that there is a lot of oxygen, like more oxygen than we could ever use. So we're going to say that it's in excess. And, you know, interesting, we don't have to write out the entire word excess. We'll just write the two letters X and S to be excess. Okay? And obviously, before the reaction has occurred, we have no products, okay, because the reaction has yet to occur. So my moles of products are both 0 in this case. Okay, so that's the before line that we have to fill in. Now, here's a couple things to remember when you're on step 2. First of all, we need to focus on the mole relationships whenever we are working with these BCA tables. So always understand the relationships between products and between reactants. The relationship in this particular reaction is a simple 2, 3, 2, 2 relationship. And it's that relationship that's going to help us fill in the change line on the next slide. And second of all, as I mentioned before, we're always going to assume if we're burning in air that there is more than enough oxygen to react. Sometimes the problem will actually tell you what that excess reactant is. It'll say like methane is burned in excess oxygen, or it'll say zinc chloride is added to excess silver nitrate. So it'll tell you what the excess material is. In this case, you just kind of have to understand that there's way more oxygen than we'd ever use. Okay. And how does that excess come into play? Well, let's think about it. Even with unlimited reds. So even if we had unlimited amounts of oxygen, so on my reds here are oxygen, my reaction will still actually be limited by my blue. So in my little analogy here, my blue is my hydrogen sulfide, and my red is my oxygen. I've got all the oxygen in the world, but something limits the reaction. Okay, we call that the limiting reactant, and that is the blue material right here. Even though I've got all these reds up top, I can only make that little bitty product right there on the right side. Okay, so we've got the before line filled in. Step 3, we're going to use ratios of coefficients to determine the change. Probably the most difficult part in the BCA table. So because we have excess oxygen, we know that we're going to use up all of the hydrogen sulfide. It's going to be totally gone. So what we do is we say we are going to lose 2.4 moles of hydrogen sulfide. Okay, we just lose it all. And to show a loss, we use a negative sign, so minus 2.4. Now the question is, well, how much oxygen will we truly use? That is where the mole ratio comes into play. So when you get to this point, you're going to do a little math on the right side of your BCA table. You'll take that original amount of hydrogen sulfide, 2.4 moles. I'm going to move this over if you don't mind. Here we go. 2.4 moles of H2S. Place that over 1. Everything should look like a nice fraction. Okay. And now you need to look at the ratios. Well, for every 2 moles of hydrogen sulfide that react, you're going to react 3 moles of oxygen. Well, we want to get rid of hydrogen sulfide because we are looking to fill in this area right here. So we've got for every 2 moles of H2S down here, we're going to react 3 moles of oxygen. Again, oxygen is completely in excess. So do we have 3 moles of oxygen? Yeah, we actually have more than that in this reaction. So I've got a mole of hydrogen sulfide on the bottom and a mole on the top. Those can cancel out. So on my calculator, I just punch in 2.4 times 3 and then divide that in half. And I get 3.6. 3.6. I don't get negative 3.6, I get 3.6. But again, since it's a reactant, we place a negative sign in front of it to show that it's going away. All right. So that's the left stuff on my change side. So what about the right stuff? Where do the 2.4s come on the right side? Well, if we are losing 2.4 moles of hydrogen sulfide, and the relationship between the moles of hydrogen sulfide and the moles of each product is 1 to 1. Like, look at it up here. It's a 2 to 2 to 2 relationship, which is the same as a 1 to 1 to 1 relationship. Then the amount of moles of the limiting reactant, hydrogen sulfide, will be equal to the amount of moles of the products produced. So we see here that there's 2.4 moles lost. That equals 2.4 moles gained for each of the products, and that again is because of the coefficient 2. Now if for some reason this coefficient 2 is different, if it's a 3, then this number would not equal that number. Okay, but that's not the case for our example here. We'll see that tomorrow. Alright, and then we'll get to the after in a second. So reactants are consumed and products accumulate, so that's where the negative and positive signs come from. All right, step 4 then. We'll complete the table by doing the after. My little line should be higher here. There we go. Okay, by doing the after, that's the change that we have. So 2.4 minus 2.4 obviously is 0. We have an excess, a total excess minus 3.6. We still have excess. We just put excess down for our excess reactant. Okay, and then 2.4 plus 0 for both of the products gives us 2.4. So we produce 2.4 moles of each of our products. We're going to emphasize one thing, that the change in the final state are not equivalent. Even though they sometimes look very similar, this state and this state are not equivalent to each other. They can be different. Okay, if there are any calculations that need to be done, you've got to complete those on the side of your BCA table. We saw this with the mole ratio. This also is true if you have to go to mass. So this previous problem was asking how many moles of oxygen would be needed to consume the 2.4 moles of hydrogen sulfide. So we weren't asking for mass at all. But what if they did ask for mass? Well, you'd have to take the amount of moles that you found for oxygen and turn that into mass. And hopefully you remember how to do that from Unit 5. That's using the molar mass of oxygen to figure that out. So lastly, here's a couple of very important things before we end. Number one, only moles go in the BCA table. Mass never goes in the BCA table. Volume never goes in the BCA table. The BCA table is only moles. It's only how many, not how much. If given mass of reactants for products, you got to convert to moles first and then use the table. And again, all that math will be done to the right of your BCA tables. All right, that's it.